Imagine we have two conductors with an arbitrary shape. Now initially, these two conductors have zero charge. If I connect a battery to these two conductors, recall that the circuit diagram for battery is two parallel lines. Now, in the circuit diagram, the longer of the two parallel lines means it is the positive terminal, and the shorter of the two parallel lines means it is the negative terminal. Now, when you connect the two conductors to a battery, the positive terminal will push the positive charges on this conductor, so eventually, this will accumulate a positive charge. And the other conductor will eventually accumulate a negative charge. And once these charges accumulate, then these two conductors will have an electric field between them. Let's assume that this battery has a potential difference of V sub AB. In other words, from this point of the battery to this point, the potential here is V sub A and the potential here is V sub B. Now, studies have shown that the accumulated charge, when we say charge on these two conductors, by the way, when you have two conductors and it is separated by a vacuum or any insulator, then these two conductors is called a capacitor. So again, a capacitor is a system of any two conductors separated by an insulator or a vacuum. So it turns out that the charge that accumulates on a capacitor, when we say charge, let's assume that this conductor has a positive charge Q. And since they are connected to the same potential difference, the other charge will accumulate the same magnitude but opposite in sign. So this will acquire negative Q. So when we say charge of a capacitor, we're just referring to the magnitude charge Q. So by convention, we're referring to the magnitude of charge Q, and we could just focus on this positive charge Q. It turns out that the accumulated charge Q is directly proportional to the applied voltage V sub EB. So again, when you increase the voltage applied to the two conductors, the charge increases as well. Now, as we all know in physics, in order for this directly proportional symbol to become an equal sign, like this, the equation must be multiplied with a constant of proportionality. Let's label that constant of proportionality C. Now, in physics, we have a special name for this C, and it's called capacitance. If I rewrite this equation, we have C equals Q over V. So this is the definition for capacitance. In electronics or in circuit diagrams, the symbol for a capacitor is represented by two parallel lines of equal length, or one of the lines is curved. So this is the circuit diagram for capacitor. Now the SI unit for capacitance is Farad, abbreviated by capital F. So based on the equation, 1 farad is also equal to 1 coulomb per volt. Now if I quickly remove this battery and the charges are retained, notice that if I put a charged particle between them like this one, then the system is able to push this charge from this direction. So in other words, the capacitor is able to apply work on this charge. And as we all know, any system that can apply work on an object possesses an energy. In a way, we can calculate the energy possessed by a capacitor, and since this is a conservative force, an electric field is a conservative force, what we're actually computing is a potential energy. Recall the definition of electric potential. The letter U here is the potential energy. And Q sub 0 here is the test charge. But if we view this charge here as the charge being transferred to one of the conductors, or the amount of charge that's being transferred to one of the conductors. So basically, if you transfer an infinitesimal amount of charge dq from this conductor, then there will be a negative dq that's going to accumulate on this side of the conductor. So basically, I can rewrite this equation as U equals QV, but if we consider the infinitesimal amount of charge that's being transferred, I can rewrite this as du v dq. To get the total energy possessed by the capacitor, we have this U equals integral of V dq. This amount of charge is integrated from 0 to a total charge Q. At this stage, we now use the definition of capacitance. Since capacitance is C equals Q over V, then I can replace potential here with Q over C. Now this is the equation for the potential energy stored in capacitors. And notice that I can rewrite this equation into other forms. For example, if I replace C here with Q over V, I'll end up with and notice that I can rewrite this equation again into other form. If I plug the definition of capacitance here at Q, so I can plug Q equals CV here and I'll end up with 1/2 CV squared. So therefore, the potential energy stored in capacitors can be rewritten as Q squared over 2C or 1/2 CV squared or 1/2 QV. Again, this is the potential energy stored in a capacitor. Now imagine we have a parallel plate capacitor. So if I have a conductor here with area A and another conductor here at the bottom with the same area A, and we connect this upper conductor and supply it with a positive charge Q and the bottom one with a negative charge. So once the conductors accumulate charge, then there will be an electric field here. So at the middle of these two conductors, we can assume or approximate that the electric field are uniform, and near the sides, the fringing is not that large. So when we have a parallel plate capacitor, we can derive another form of capacitance for a parallel plate capacitor. So assuming that this is in vacuum, so if we calculate the electric field at the middle of these two conductors, at the middle part, we could actually assume that one conductor is an infinite surface charge, so it has an electric field with magnitude sigma over 2 epsilon naught. And also, the conductor at the bottom contributes an electric field that's going downwards, and it has a magnitude of sigma over 2 epsilon naught. So to represent the total charge contributed by each surface or conductor, so the total electric field is sigma over 2 epsilon naught plus sigma over 2 epsilon naught equals sigma over epsilon naught. And if I try to expand sigma over epsilon naught, recall that this is a surface charge, so this is actually equal to Q over A. Now, also from our previous videos, potential difference V sub AB can be rewritten in terms of electric field. And if this electric field is uniform, we could just rewrite it as ED. In our case, the D here is the distance between the two parallel plates. And the electric field is the electric field between them. So in a way, the electric field is also the total electric field that's being sandwiched by the two conductors. If I now write the definition of capacitance, C equals Q over V. The potential difference here is the potential difference between the two conductors. So I could just write AB. Since earlier I assumed that this is being brought to a potential of V sub A, and the lower conductor is brought to a potential difference of V sub B when it is connected by a voltage supply. And because of this, the potential difference between the two conductors is V sub AB. And if I plug the definition of V sub AB on this equation, I'll have Q over ED. And if I plug the electric field between the two conductors, I'll end up with Q over epsilon naught AD. We have the final form of epsilon naught A over D. This is the capacitance of a parallel plate capacitor in a vacuum. Now, while we have this figure, let me go back to this potential energy. Okay, let me delete this part. Let us compute for another useful quantity called energy density. Energy density is equal to energy divided by volume. So this is also equal to our energy here, U, divided by, for example, this system has a volume of area times the distance between the two capacitors, D. So rewriting it here, U is equal to, we can choose any of the three, so I'll just write 1/2 CV squared divided by AD. And we know that C is equal to this one, so 1/2 epsilon naught A over D V squared over AD. So this is equal to 1/2 epsilon naught B squared over D times D squared. And we know that V equals uniform electric field times displacement. So this is equal to 1/2 epsilon naught E squared. We now derive the electric energy density of a capacitor in a vacuum. And we can represent it with small u. Let's return to our capacitor. So initially, we have a vacuum between the two conductors. Now, experiments show that if I have a volume of an insulator, a solid insulator, and we call this type of insulator dielectric because it can be polarized. So when I insert this slab of insulator between the two charged conductors, each of their molecules may realign their charge temporarily, so they can be polarized. So we call this type of insulator wherein their molecules can be partially polarized as dielectric. Experiments show that when this is inserted in our capacitor, something like this, then its capacitance based on experiments increases by a factor of K. So if this capacitor in vacuum has a capacitance of C sub 0, then when we insert a dielectric on that same capacitor, it has now a new capacitance C. And based on experiments, it increases by a factor of K. We call this constant here K as the dielectric constant. Now notice that if I plug the equation for capacitance in a vacuum here, so I'll end up with epsilon naught A over D. And if I try to regroup the constants here, we could actually label this group of constants as C equals epsilon A over D. And we have a special name for this epsilon, and it's called permittivity. So this is actually the definition of permittivity. Again, the definition of permittivity is permittivity equals dielectric constant times the permittivity of free space. Consider these two capacitors. This capacitor here has a capacitance of C sub 1, and this capacitor at the bottom has a capacitance of C sub 2. When any electric component are connected in such a way only one current passes through them, then they are connected in series. In circuit analysis, it is easier to do calculations when we try to calculate the equivalent value of two similar components. For example, if I try to connect this with a power supply, so let's assume that the potential here is V sub A due to the battery, and here V sub B. So in a way, the potential difference here is V sub AB between these 2 points. We would like to calculate the equivalent capacitance of the two capacitors in such a way they could simplify the circuit like this. So let's analyze the situation. When this battery pushes the positive charge on this wire, this part of the capacitor acquires positive charge. And let's assume that the charge accumulated on this upper conductor of C sub 1 is positive Q. And because of this, it will attract the negative charges on the lower conductor of C sub 1, and it will have the same magnitude, negative Q. And because of this negative Q, it will attract the charges on the upper conductor of C sub 2. What will remain are the immobile positive charge on this conductor, and because of such transfer of charges, this will have a charge of positive Q that is in equal magnitude with negative Q. And because of this accumulated positive charge, it will also attract the mobile negative charges on the lower conductor, and it will have the same magnitude, negative Q. So in a way, the two capacitors have equal magnitude of charge, Q. Now the capacitance for C sub 1 is equal to Q sub 1 divided by V sub 1. And the capacitance for C sub 2 is equal to Q sub 2 over V sub 2. But we already established the fact that they have equal charges, meaning to say capacitors in series connection have equal charges. So this becomes Q over V sub 1, and this one is Q over V sub 2. In other words, we just represented Q sub 1, Q sub 2 with just a single variable Q since they are equal. And if capacitor 1 has a potential difference that can be represented by V sub 1, and capacitor 2 has potential difference represented by V sub 2, then based on this diagram, V sub AB is equal to V sub 1 plus V sub 2. So by conservation of energy, V sub AB is somewhat distributed at capacitor 1 and capacitor 2. So we cannot assume that the distribution of V sub AB is equal because these two capacitors might have different values of capacitance. So notice that if I divide both sides with Q, notice that from this equivalent capacitance is equal to charge over the entire voltage of the battery. Therefore, this is the equivalent capacitance, 1 over C sub 1 2, and V sub 1 over Q is this one. So 1 over C sub 1 plus 1 over C sub 2. To generalize this expression, if we represent the equivalent capacitance of capacitors in series with C sub EQ, then 1 over C sub EQ equals 1 over C sub 1 plus 1 over C sub 2 plus 1 over C sub 3 and so on. Let's now derive the expression for capacitors in parallel. Let's assume that this capacitor has a capacitance of C sub 1 and this one with C sub 2. Let's apply a potential difference of V sub AB to C sub 1 and C sub 2, capacitor 1 and capacitor 2. Now apparently, capacitor 1 and capacitor 2 experience the same voltage V sub AB. If capacitor 1 has a voltage of V sub 1 and it is in parallel connection with another capacitor, then they experience the same voltage V sub AB. So again, when capacitors are connected in such a way they share the same voltage, then they are in parallel with one another. They are connected in parallel with one another. So in circuit analysis, calculating the equivalent capacitance of two capacitors makes the calculations easier. So in a way, we would like to get the equivalent capacitance of these two capacitors in such a way we could represent the equivalent capacitance with Q over VAB. When an electronic component is in parallel connection with one another, notice that when current flows here at this node, the charges are divided into two. So when total charge Q moves through this path and then reaches this node, it is now divided into Q sub 1 and Q sub 2. So in a way, the original amount of charge coming from the battery is now divided into two. Q sub 1, the charge that accumulates on capacitor 1, and the charge that accumulates on capacitor 2. So capacitor 1 has a capacitance of Q sub 1 over V sub 1, but since V sub 1 is equal to V sub AB, then I'll rewrite it as V sub AB, and C sub 2 equals Q sub 2 divided by V sub 2, but since V sub 2 is equal to V sub AB, then I'll write V sub AB. Now notice that if I divide both sides of the equation with V sub AB, I'll end up with an expression for equivalent capacitance. And Q sub 1 over V sub AB is equal to C sub 1, and Q sub 2 over V sub AB is equal to C sub 2. So to generalize this, when you have a lot of capacitors in parallel connection, their equivalent capacitance is equal to the sum of the values of individual capacitance. Let's try to solve OpenStax University Physics Problem 33 from the chapter about capacitance. So the problem requires us to find the total capacitance of this combination of series and parallel capacitors. So our strategy is to first get the equivalent capacitance of these two capacitors. And I'll end up with this kind of setup. So let me rename the capacitor with 10 microfarad capacitance as C sub 1, and then this one with C sub 2, then this one with C sub 3. So when I calculate first the equivalent capacitance of C sub 1 and C sub 2, I'll end up with C sub 1, 2, and now it is in series with C sub 3. Then I'll just calculate their equivalent capacitance like this. So let's start with C sub 1, 2. So since C sub 1 and C sub 2 are in series with one another, their equivalent capacitance C sub 1, 2 is just their sum. The equivalent capacitance of C sub 1, 2 and C sub 3 is equal to 1 over C sub 1, 2, 3 is equal to 1 over C sub 1, 2 plus 1 over C sub 3 since they are in series with one another. So simplifying this expression, 1 over C sub 1, 2, 3 equals C sub 3 plus C sub 1, 2 over C sub 1 to C sub 3. And I'll end up with C sub 1, 2, 3 equals C sub 1, 2, C sub 3 over C sub 3 plus C sub 1, 2. And then I'm going to plug this expression for all the C sub 1, 2 here. So let me rewrite it here. C sub 1, 2, 3 equals C sub 1 plus C sub 2 times C sub 3 divided by C sub 1 plus C sub 2 plus C sub 3. So plugging in the values, C sub 1, 2, 3 equals, C sub 1 is 10 microfarads plus C sub 2 is 2.5 microfarads multiplied to C sub 3 which is 0.3 microfarads divided by their sum. C sub 1 is 10 microfarads plus C sub 2 which is 2.5 microfarads plus C sub 3 which is 0.3 microfarads, and the final value is 2.93 times 10 raised to negative 7 farads, or C1, 2, 3 equals 0.29 microfarads. Let's answer OpenStax University Physics Problem 77 from the chapter about capacitance. A spherical capacitor is formed from two concentric spherical conducting spheres separated by vacuum. The inner sphere has radius of 12.5 centimeters and the outer sphere has radius of 14.8 centimeters. A potential difference of 120 volts is applied to the capacitor. What is the capacitance of the capacitor? What is the magnitude of the electrical field at R equals 12.6 centimeters just outside the inner sphere? What is the magnitude of the electric field at R equals 14.7 centimeters just inside the outer sphere? And for a parallel plate capacitor, the electric field is uniform in the region between the plates, except near the edges of the plates. Is this also true for a spherical capacitor? I have already drawn the figure here. The inner spherical conductor has a radius of r sub 1 which is equal to 12.5 centimeters. R sub 2 has a radius of 14.8 centimeters. And the potential difference between them is if inner conductor has a potential of V sub A and the outer conductor has a potential of V sub B, then their potential difference is 120 volts. The distance between the two conductors is equal to R sub 2 minus R sub 1. If sphere 1 has a higher potential than sphere 2, then you can actually observe an electric field radiating from the inner sphere and terminating at the outer conductor or outer sphere. Now in part A, we would like to determine the capacitance of this capacitor. So the formula for capacitance is C equals Q charge over potential difference. And as we all know, potential difference can be rewritten in terms of electric field. And the electric field we're talking about radiates from R sub 1 and terminates at R sub 2 based on the figure. So V sub AB, if we try to use Gauss's law to calculate for the electric field, if I try to draw an imaginary surface here, notice that the only enclosing charge by the Gaussian surface is from the conductor 1 or the inner conductor. From previous videos, the electric field that we will be able to obtain using Gauss's law is equivalent to the electric field due to a point charge. So R sub 2, R sub 1, and the electric field due to a point charge Q over 4 pi epsilon naught R squared. Remember that R is from center of the sphere to our Gaussian surface. Notice that this electric field has a direction of R hat, and this dr is obviously radiating from the center, so it also has a direction of R hat. So R hat dotted to R hat is equal to 1. I already skipped that part. That's why all the vectors here are gone. So isolating all the constants, now plugging this to the definition of capacitance, Q over V over A sub B, plug it here. We'll end up with C equals 4 pi epsilon naught R1 R2 divided by R sub 2 minus R sub 1. To get the numerical value, we plug in the given. The capacitance is therefore equal to or C equals 89.5 picofarad. Now for part B, what is the magnitude of the electric field at R equals 12.6 just outside the inner sphere? So we could just use Gauss's law here. So this is the Gaussian surface. And from previous video, this is just equal to the electric field of a point charge. Notice that we don't have a value for Q, but we already have a value for capacitance. So we could just plug the definition of capacitance here since we also have a value for voltage. And R here is 12.6. Plugging in the values, and the electric field is equal to 6082.89 Newton per coulomb or volt per meter. Now for part C, what is the magnitude of the electric field at R equals 14.7 centimeters just inside the outer sphere? Again, if I try to draw an imaginary Gaussian surface here, I'll end up with this same equation, but with a different value for R, and that R is 14.7 centimeters. So plugging in the values but just updating this R with 14.7, I'll end up with 4,469.10 Newton per coulomb or volt per meter. Now for part D, for a parallel plate capacitor, the electric field is uniform in the region between the plates except near the edges of the plates. Is this also true for a spherical capacitor? So if you try to observe the electric fields here, the electric field vectors are radiating outward. Therefore, for the regions near the center of the capacitor, the electric field density is greater than the outside. Therefore, it's not uniform and the answer is no. Don't forget to like this video, subscribe to my YouTube channel, and hit the notification bell button for awesome updates. Thank you for watching!